And now what we need to do is apply our skills in trigonometry to be able to get the x and the y components. So some of you may have already recognized that for this 90-degree angle, the 3, 4, 5, if that's 90, we must have all angles add up to 180. You might already know that this is a 60-degree angle, and then this is going to be a 30-degree angle, but I'm going to represent this with the value phi. Okay, and I'm going to let you verify that if needed, but I think you should be pretty comfortable with this idea. It should be things that you're familiar with at least. So if I know the angles then, and I know the value of the electric field in this r direction, so what I'm going to do is let me just redraw this triangle, and I'm going to replace it with the field values because that's what I'm asking us to do. So what I'm saying here is that it's not really the r that I'm interested in, it's E vector, the electric field vector, which we've already solved. So I'm just going to copy this down. 3.6 times 10 to the 8. Okay, and that's volts per meter. And that means that this must be my y component, and this must be my x component. So I can label that as EY, and I can label this as EX. And these are the actual vector components that I'm looking for E. And the basic idea here is that just like r squared equals x squared plus y squared, well, this also implies that the vector E is going to be the square root of these two components. So EX squared plus EY squared. So we're getting pretty close to getting all the information we need to be able to get those two components, x and y. Or I should say EX and EY. So I'll go ahead and put these angles back in for phi equals 30 for this angle, and then this would be 60. We have lots of options to be able to calculate EX and EY. So let's use the familiar property. Let's say sine of phi equals, if you remember, it's the opposite, which is going to be EY, divided by E. So in this example, we know that phi is 30, so we'll say sine of 30 degrees. I'll make sure we know it's degrees, and I'm going to bring the E over here, is going to equal EY. So is there any missing value? We're trying to solve for EY in this case. We know the value of E, it's right here, and we can calculate what sine 30 is. So let me just flip this around so I can keep the variable that we're solving for over here. And we'll go ahead and bring up a calculator, or you might simply remember the values of sine 30 either in radians or degrees, and we can calculate it almost from memory. So that would be 1/2 times the value of E is 3.6 times 10 to the 8. And that's going to equal half of 3.6 is going to be 1.8 volts per meter. So there's one component, EY. And now we'll make some space over here, and we'll go ahead and solve for X, for the X component. So to do that, we could go ahead and use you could use 60 degrees, you could use 30 degrees. I'm going to go ahead and say cosine. We know that cosine of phi is going to equal the adjacent component. So this is going to be EX divided by E. And if we just rearrange this, I'm going to say EX on this side. And I'm skipping a couple of steps here. And that's going to be 0.866 to 3 decimal places times 3.6 times 10 to the 8 which is equal to let's just say 3.1 volts per meter in the X. And with that, we now have everything we asked for, in that we solve for the electric field as a vector. In this box here, I'm showing it in the R hat convention. And then we also broke it down to its individual constituent components, EY and EX. And one of the important things that we'll be coming back to later on is this very important concept of the electric field is being made up of components. And what we'll see later on is that it turns out that this holds up for any collection of point charges, where we can break the constituent components down for all of the individual source charges and calculate the combined electric field, which is very important to be able to handle large and complex problems coming up. Thanks for watching.